Then just minimize it.
La verdad no. Acuérdate que solo
Maximize that one. Okay.
Decide que.
No,
que-
pero
Ponle en view, ahí está arriba. En view options, no, junto a lo verde. Ponle side by side, lado a lado. Y luego destaca para todos. Ah, bueno, no, en vista, en el cuadrito de la esquina, arriba, quita eso. Ahí ponle solo, ajá, ese. Y destine a Daniel Oblak.
Bro.
I'm gonna write notes next to the 543 assignments. I still have them.
En un minuto.
Yeah.
It will fall.
You're gonna see me running around just trying to escape this.
Okay, you moved too fast, I think.
You red shift.
Well, if you want the camera to follow you around, you have to look at the camera and just put your phone right here. You're not gonna do that. Well, everybody's gonna be able to see.
No,
Closer, right? I don't know where it is.
yeah,
Yeah.
a little.
Your left? Yeah, there. I think that's ready. I think it's ready.
Good to share down there.
No se ve ahí abajo.
A lo mejor si le pusieron multiplicar pantalla.
Debe de ser tú. En la pantalla. Ahí. Si quieres, ya empieza.
Welcome to Eclexis, the 23rd edition of the International Symposium on Physics. We ask all participants to keep the microphone off during the entire session to avoid interruptions. For our Zoom audience, in case of any inconvenience that may arise during the session, we ask you that you send a direct message to the staff who have the name Eclexis staff in this session. If you would like to ask Dr. Oblak a question, please send it as a direct message to Eclexis Q&A. For those of you who are attending in person at the Congress Center, you can send your question to him through our staff. Today, we're joined by Dr. Daniel Oblak, professor at the University of Calgary and principal investigator of the Quantum Cloud Laboratory. His research in communications and quantum networks has included implementation of quantum memory, photon sources, and detectors, and optical to RF transducers. Welcome, Dr. Oblak.
Thank you very much. All right.
Yeah.
All right, yeah, thank you so much to everybody here, to especially the organizers. It's a real pleasure to be here. I haven't traveled outside of Canada for 2 years, so it's like, oh man, it's finally I'm getting out of the country. And so this was really a great timing for for this invitation. And yeah, it's a great event so far. Lots of things going on, lots of good speakers, and a very broad introduction to physics, which I really think will give. I mean, I hope will give all the undergrads here a real taste for all the things that are possible in physics. So I'm going to talk about. So this is a tutorial, so we're going to keep it sort of fairly simple, or we're going to start in something that I hope everybody can follow really along with, and maybe we'll go a little bit faster towards the end, that things get a little more complicated. But overall, I hope that this is supposed to give a little bit of a background of the field, which is the field that I'm in, which is quantum communication, and to understand sort of some of the basic principles, so that next time you hear talk about quantum, various things in quantum communication, you'll say, like, I know what that is about, and I've heard about it before, and you can easier follow it. And maybe it will give you the taste of thinking, like, I want to do this because this is fun. And I will have a talk tomorrow, which is more on the research side, a little more advanced stuff. So interested in that one too. All right, so I think I'm going to be the button presser here. Okay, so yeah, quantum communication, and as I called it, as a subtitle, a tutorial to some of the random things I decided that are important, because I can decide exactly what I think is important and what I'm going to cover here. The field is obviously big, and I can't cover everything in the field in even 1 hour and 15 minutes. So we're going to scratch the surface, and I've decided what I want to tell. And so, yes, I'm at the University of Calgary, as it says there, in the center, and this is almost visible here, but Institute for Quantum Science and Technology, and I call my lab the Quantum Cloud Lab, or the Q-Cloud Lab, because, quantum on the cloud is like networks, right? Okay, so, okay, so we gotta get through this, all of this. Yeah, so I'll keep this up every time we change a section, so you'll see where we are. I'm gonna start with some opening remarks about quantum science in Calgary, just to say what we are, who we are. Most of you probably know that Calgary is in Canada, but not that much else about it. So let me talk a little bit about it. But before that, I'm going to take the opportunity to just say who I am, where I come from, and what I've been through to get here. So I started with a bachelor's in mathematics and physics at Aarhus University, continued to a master's in physics, that's in Denmark. And then my supervisor decided to move halfway through my master's, and then I followed him to Copenhagen University, the Niels Bohr Institute, which is a very nice name. And actually, the fun thing is that a lot of institutes are named after famous physicists, but this one was actually founded by Niels Bohr Institute, although he called it the Institute for Theoretical Physics, and then later on it was renamed. So actually, and if you do in my PhD defense, I was in an auditorium where you have photos of all the greats of quantum physics sitting on these wooden hard benches, but it's a special historical place, so a really nice place to have been. I had visited the Australian National University and saw a lot of kangaroos and birds and did some interesting physics there. And then I moved to University of Calgary first as a postdoc, and then I transitioned into assistant professor, which is what I am now. Well, what do we do in Calgary? What is the University of Calgary? So yeah, somebody asked me when I arrived how many students there were, and I couldn't answer that, which is embarrassing. But here it is, 33,000 students. We're just a little over 50 years old, so we're actually a pretty young university, and 5 campuses in various places and 14 faculties. And there's a website for it there. Quantum at University of Calgary is centered around the Institute for Quantum Science and Technology, and it's science institute. So, it's not just physicists, there's computer scientists, mathematicians, physicists involved in this institute, because, quantum pops up in many, many different places, not just in physics. I mean, the mathematics of quantum is an important field. And when you talk about quantum computing, obviously, computer science is important, right? So we have these research fields here. You can look more about the Institute by visiting that link there. And sort of a recent initiative at Calgary is something called Quantum City. A little bit of a boring name, but okay. But it's an exciting thing because nowadays, more and more quantum stuff is about partnering with industry, partnering with companies. And so the idea is to get companies to actually set up business in Calgary. And the first company that really sort of is going to come in is a company called Emphasis. You may not have heard about it, but it's an Indian tech company. And they're setting up and funding various aspects of this quantum city. And we're going to get more people there. Amazon Web Services actually has decided to put some operations in Calgary, and they may have some of their quantum stuff also going up there. So lots of movement in quantum in general. It's can get a bit tiring with all the opportunities. There's so much going on. And as I said, this is my lab here, and I'd say putting quantum in the cloud, I guess. But this is from my website. And if nothing else, you want to see some pretty pictures from the surroundings that all are taken by me, go to there and see. This is that's Lake Louise down there. So in the fall, so lots of nice things to see as well. If you don't want to stay in the lab all the time, here's all the social media stuff and websites. So you can hook up to that, follow whatever you want, and see what we're doing, sort of in general. So very, very brief introduction before I go into the details, just to give an overview of the field of quantum information. What that is, we generally categorize it into 3 pillars. There's the quantum computing part, which is the one that gets a lot of attention, obviously, because it is such a groundbreaking, paradigm-shifting technology, and lots of companies in that. We have quantum sensing, which is a very broad term, covers really anything from MRIs to using ghost imaging and scanning tunneling microscopes. Those are all really sensors based on quantum mechanics. And then we have quantum communication in the middle there, and that's the one that I'm interested in, or that we deal with. So it's about using quantum mechanics for transferring data or communicating either between people or units or different quantum devices. For example, sensors or computers could be connected via quantum computers, with quantum communication links, right? So really broad overview. You can hear more about this then on my talk tomorrow, but this is all the stuff we're trying to do. Quantum networks, these are quantum links, the yellow ones, and then different places, satellites, quantum memories, light sources, and maybe some kind of superconducting devices that can serve as look like quantum computers. All about linking those up, and this is Calgary with the mountains in the background there, and so we're trying to do that within the Calgary. And who's trying to do that? Well, this is us. It's a little bit outdated. There's actually a few more people in the group here, but we're about 20 people in the lab, and from all over the place. But maybe can't recognize, but I don't have anybody from Latin America. So it would be nice to have more people from the same continent or from where we are on the internet. Okay, blah, 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 done with that, right? So now we get into the actual tutorial. So I'm going to start with introducing quantum mechanics a little bit, just so that we're on the same page with some of the basic sort of principles, so that we can talk about the rest of the stuff, because then I'm going to go into quantum information, quantum communication, and I'm going to cover quantum key distribution quite a bit, just because it's an interesting application of basic protocol in quantum communication that I think a lot of, will be easy to understand once we get through the rest. And then we'll see how we get through the rest. I would like to go and talk about quantum teleportation, but we do need to get into entangled states before that. So we'll see how far we get. But I'll try to speak fast yet clear. Okay, so what is quantum mechanics? Well, quantum mechanics typically is a way we describe really tiny stuff. So right about here, where we're talking about atoms and above, it's not particle physics, but it's sort of in that range, just above that, and then everything on the atomic scale. Here is, there's a couple of important moments in quantum mechanics that defined it. If everybody heard the previous roundtable, there was discussion about, the revolutions in quantum, revolutions in physics or in science in general. And there was a revolution happening in physics around the beginning of the last century, so 1910s and 20s and into the 30s. And that was when people discovered that something more was needed to describe the world. And all the people that are relevant for that, almost all of them can be in this picture. The first thing was that people looked at the emission of light from what we could call a black body. So basically something like the sun, an object that only emits light depending on its temperature. And they found that, well, something doesn't add up, because according to the current models at that time, the energy emitted by such an object should be infinite. And it's not quite right. I mean, obviously that's not what happened. So something was missing. And so Max Planck, he found a way to solve this, and he solved it by requiring that energy packets or energy can only be emitted in certain discrete bundles or quanta, as it came to be known. And that gave, it went from the energy or the spectrum predicted to go to infinity for short wavelengths to something that actually cuts off at short wavelengths. And so this is the first place where, without really knowing why, the notion of quantized something, in this case energies, was introduced into physics. There was no underlying reason, which was kind of a problem. So clearly something was just missing, and people hadn't yet figured out exactly what it was. And by the way, if you have questions or like something's unclear, like raise your hand, and I'm happy to sort of do interactive throughout the lecture. Okay. He won a Nobel Prize for that, so good for him. Next person to come around was Einstein, because unlike before he went into general relativity, he looked at the problem of what's called the photoelectric effect. And there was this weird thing that usually you think that the more intense light you put in, like if you push a car harder and harder, or you have a water jet you're pushing on a ball, let's say like that, the more water you spray at it, the faster it will go. But when it came to light and shining on metal where electrons were emitted, it didn't matter how much light you put on, the electrons would always come out with the same speed. So somehow it wasn't proportional to the intensity, but it turned out it was proportional to the wavelength. And that all fitted with a theory where you said that the energy of these incoming light was indeed coming in some unit of energy that depended on the frequency. And it turned out that this constant here was the same one that Planck found. So that was cool, and therefore he got a Nobel Prize too. Actually, he got the Nobel Prize for that, not for the general relativity stuff that he did later on. Fortunately, I don't think you can win a single Nobel Prize in a single field, so you have to go into another field if you want to collect them. Then next comes along is, of course, somebody who's dear and familiar to me, which is Niels Bohr, and he addressed the fact that something was wrong with the way we describe atoms. They found out that atoms consist of some electrons, a negatively charged thing that orbits something very dense in the middle, and most of it is air. But usually when you have two things that are positively and negatively charged, they will attract each other. Okay, so if something is spinning, then maybe you can prevent that, because like planets spinning the sun, we can keep away from the sun because we have an angular momentum. But then the problem is that the electron should be emitting radiation and lose energy, and that also doesn't happen. So what's going on? Well, okay, so we say that it doesn't happen because electrons can only exist at certain energy levels, and those discrete energy levels you can move between them, but only in jumps. And again, one could show that the radiation emitted from atoms followed these jumps, and based on this formula for the frequency and of the light and the energy of the light, one could actually relate the wavelength of the light to what the energies would say, and then you could say that fit the theory as well. And so everything seemed to come together into that different physical phenomena required some kind of quantum levels, some discrete levels. I mean, in Greek, quanta just means a unit or a packet of some kind. So whenever you say something is not smooth, but comes in lumps or chunks, then you say it's a quanta. Okay? Surprise, surprise, a Nobel Prize. And then a lot of other things happened. A whole bunch of other people were involved in quantum mechanics. Schrödinger, Dirac, Heisenberg were involved in a lot of actually just getting a more concrete and complete picture of quantum mechanics, like the mathematical aspects of it, getting on a solid foundation with the Schrödinger equation or the Heisenberg equation, which are sort of the thing that now in textbooks is being taught is how you teach quantum mechanics. Okay. Coming next. Lots of Nobel Prizes. Okay, so here is where we're going to start with quantum mechanics. We're going to say that a quantum system is represented by a wave function. And so everything about the wave function, everything about the quantum system is given by that, by this wave function. And how do we interpret the wave function? Well, the wave function describes the probability amplitude of measuring some outcome of a measurement of the system. So, it's very generic because the wave function can be represented as describing different properties that can be interrelated. It could be the position of a particle, for example, as we'll see next, but it could also be the spin or the angular momentum, or the polarization of light. Basically, we're just saying that anything about the quantum system is given by the wave function. And we write in these curly brackets, that's called Dirac notation. So whenever we see that, we just say that's a quantum state, right? To be precise, just for those who are nitpicking on this, is that, well, we're looking at the square of this amplitude is what gives us the probability. So we take the square of the wave function, that gives us a probability, because the wave function actually is a complex quantity, so it can have a phase and live in complex space, which is important for everything in quantum mechanics later on. Okay, so here's an example. Here's our wave function, and this is the amplitude, so we can go negative, no problem, because once we take the square of this, everything will be positive, and probabilities make sense. And so the other problem in quantum, or the other really important concept in quantum mechanics is then that, which will be very important for quantum information, is that once you measure a quantum system, that measurement changes the system or changes the wave function more particularly. And this is where all the discussion about what does a measurement in quantum mechanics actually mean comes in. And that is a very, very big problem that people haven't really understood what it is. So for now, we're just going to use this picture where we say that the wave function collapses. It's called the Copenhagen interpretation. So I'm legally bound to follow that one as a Danish person. The way we understand it then is, I say, this is our initial wave function. Well, then we do a measurement of it, and we measure this particle or the system to be here. And once we measured it to be there, we know it's there, so the wave function has to reflect that. So now the wave function will be something that has a peak just around that area, and the rest is not there anymore. That was the initial wave function, and now this is the one after the measurement. So we change the system by measuring it, and that's another important concept from quantum mechanics. Okay. Now we can ask yourself, since the wave function describes a system, we can ask ourselves, what kind of things can we say about a system, or what properties does a system have? Of course, it depends what system you have. We're talking about quantum communication. We're going to use light a lot because light travels fast. So light is the sort of the photon as the unit of the particle of light is going to be our choice of system for the most part here today. So we can ask ourselves what then characterizes a photon. If we wanted to write the wave function for a photon, what kind of things would we express this wave function in terms of? So, many things, right? Obviously, there's the wavelength or the color frequency of the photon. which way does it go? A photon going this way and that way will obviously be two different photons. They can't do both at the same time. So, we can have that characterize the direction. We can have sort of like the shape of the photon. If you took a cross section of it and looked at it on a camera, then what would it look like? Different shapes of the beam, the polarization, obviously, which way is the electric field oriented of the electromagnetic wave that this photon is. And we can also look at the profile of it, like is it a very wide photon, like take this long duration, is it very short? Does it have an orbital angular momentum? This is maybe less familiar to all people, but photons or light can also have an orbital angular momentum. So a whole bunch of things that light can be characterized as. We're going to focus on polarization just because it's the easiest one to understand and it's very simple. And a lot of the initial experiments and protocols in quantum informations were done using polarization. So we're going to use that. It's the direction of the electric field. We're going to represent it. So if this goes up and down like this, we're going to write it as an arrow like this going up and down. That's then the polarization of the light and the polarization, state of the light. Okay, so what's some of the properties of polarization? And this is funny, right? Because this is basically the first couple of slides of Tony Leggett's talk yesterday. So, I feel like I'm on the right track if I'm doing the same as he does. So there's a validation that that's a good way to approach it. So when we're talking about polarization, we could ask ourselves, what happens or what happens when we when we send it through something that only allows a single polarization to go through, because that could be a way of determining what is the polarization. You put some light through a polarizer that will either reflect or transmit the light. Well, you will know, depending on whether it was reflected or transmitted, what was the polarization of the light. So this gives you a way of measuring it. We have to understand what happens to that polarized photon then when it hits one of these polarizers. And we're going to start out with just not talking about photons, but just light as a classical wave or something with an intensity I. So let's say we have this light that's polarized at an angle theta, and the input intensity is I in. Then at the output, the intensity will be proportional to the input intensity, and then the cosine squared theta. So basically, if it's aligned, if theta is 0, then everything will go through. If theta is 90 degrees or half, then everything will be blocked, right? So that's how we can describe light being transmitted through a polarizer. And so, yeah, we can have different specific interesting angles are the ones where we have like everything going through, nothing going through, and exactly half of it going through. That's where we have a 45 degrees angle. So that's where you filter it half of the light. And those are all important ones later on when we're talking about quantum communication. So next. Right. Okay, so how do we convert this into quantum mechanics? Because if we say that the quantum mechanical description of light is in terms of particles of light, so photons, well, then you either have a photon or you don't have a photon. So you can't split it by some random cosine squared of a theta fraction, because then the energy would be different. Obviously, you'd have less of it, but that's not consistent because the energy only depends on the frequency. So you're not changing the frequency with the polarizer, so it just doesn't add up. So something else must be happening. And the correct way to look at it is now, well, it's kind of in the hint when we've said that the wave function describes probabilities. Well, this kind of has to be expressed in terms of probabilities too. So instead of saying that, some fraction of the photon comes through, we say that there's a certain probability that the photon makes it through. If initially the probability is 1, then now the probability is equal to cosine squared of theta for the photon to make it through, and 1 minus that for it to be reflected. So that's actually a very simple way to express the classical experiments or the classical results into the quantum mechanical picture. And of course, this translates very well if you had a billion photons, which would be more or less classical, it would give you exactly the same result, which is important, of course. When we have known result that we want to reproduce with a new theory, the two have to add up in the regime where they should give similar results. Okay. Right. So at these specific angles here, 0, 45, and 90, we have then the probability of the photon making it through is either 1, 0, or a half if it's at 45 degrees. Okay. Right, and so then we go back a little bit to the Copenhagen interpretation of this. We say that, you know, if once we measure a quantum state, we've changed it such that it agrees with that measurement. So let's say we had a photon that was measured at 45, or that was prepared at 45 degrees. Say that is the quantum state. I just say that you know, it is at a 45-degree angle polarization. Well, then we know that we have, if we look at the polarizers, we have 50% chance for it coming through. If it's coming through, we know that it has this polarization here, the horizontal. And then we know that after the polarizer, now it is a horizontal or vertically polarized photon. It changed to be that because that's the only way it could make it through the polarizer if it was vertically polarized. If on the other hand, we didn't measure it coming through, then it was probably reflected. And that means that now that reflected photon has changed to be a horizontally polarized photon. Of course, if you look at the probabilities, there's a 50% chance of this happening and a 50% chance of the other thing happening. So they're equal at this, in this case, where it's at exactly a diagonal polarization. But the important thing is to note that the polarization actually changes due to the presence of the polarizer. Yes, so warning, warning, don't measure without thinking. So here's a picture, for example. If we have a photon, some interesting consequences of that. So if you have a photon here that's polarized at 90 degrees, notice I make this little wiggle here for a photon here, I think that represents it quite well. Then you have a polarizer now that's vertically polarized, or will allow vertical polarization to come through. Well, then the probability of getting light this photon through is 0, right? Because they're orthogonal. But how can you get light through here without changing anything else? You're not changing this one, you're not changing anything there. How can you get light through? Does anybody have any idea of that? Almost. Yes. What? Yes. And what angle would you choose, or what kinds of angles? Diagonally. Something like this. Thank you, I got it right. So what happens here is, if you remember that this changes the polarization, then what you have afterwards is that now you have a photon that's polarized by 45 degrees, if it makes it through. Of course, there's a 50% chance that it gets reflected, but there is half a 50% chance that it makes it through. And in that case, now it's polarized at 45 degrees. And since it's polarized at 45 degrees, well, there's a certain probability that it can make it through the next one. There's a 50% chance that this photon makes it through. So half times half give you a quarter, right? So suddenly, by inserting something in between without changing the input or the final polarizer, you got light through. This is Malice's law, and works also for classical. But it's more interesting when you think of it in terms of probabilities, because it either happens or doesn't happen. Whereas classically, you could say that, you know, you're somehow changing a ratio. It's just a proportion, some ratio of the light that comes through. But when you talk about probabilities, it's actually really remarkable, and it's a good illustration of the fact that the measurement changed this out, the photon afterwards. So it really is a different photon once you have done this measurement. Okay. So that covered the basics, introduction to quantum mechanics, at least what we need. Obviously, for those of you who have taken the quantum mechanics, of course, know that there's a little bit more to it, but you know, this is all we need for now. So we're going to talk about the basics of quantum information. So what is quantum information? Let's just get that started. Well, if you look at classical information or classical IT stuff, we have bits, zeros or ones, and we put them onto hard disks, or, well, this is ancient right now, I should change this. And so what is the quantum version of that? Well, we take this and we encode it as qubits, so quantum bits. And for that, since we're talking about quantum systems that encode these zeros and ones, we need, something like atoms or more interesting sort of semiconductor devices, lots of different ways of doing that. But basically, we're taking something that is described by quantum mechanics and find two suitable states and choose one of them to be 0 and one of them to be 1. And the interesting thing is that whereas here we have 0 or 1, when we're talking about qubits, we have 0, 1, or we can have 0 and 1. And we'll explain that a little bit, but that's where the interesting part comes, because that allows you something rather different than you can do with just classical information. Okay, so examples here, we could say, well, we have polarization states, or we could say that the 0 is encoded in a vertical photon, and the 1 is encoded in a horizontal photon. That could be one way of encoding your quantum bits. And it's important that these two ones here have to be completely orthogonal. So if you measure a vertical photon, we can say that we definitely don't have a horizontal photon. We can see that by putting in a polarizer, which will let this one go through and completely reject this one. So they're clearly orthogonal, and that's important. We have to not have any ambiguity about what is a 0 and what is a 1. Another thing you could think of is in atomic systems. Well, in atomic systems, we have energy levels, so we could choose like the different energy levels to represent the 0 and the 1. For example, here the primary quantum numbers of the hydrogen atom could serve as the energy levels that describe the 0 and the 1, right? So, your imagination sets the limits for what can be a 0 and a 1, what can represent a qubit. Anything that is described quantum mechanical, where you have distinct orthogonal states, can be used as a qubit. What can qubits do? Well, as I hinted, they can do more than classical bits. And the thing that was the 0 and 1 is what we called superpositions. So if you now describe this psi here is how we always write generally the quantum state, if we just want to have a general expression. So we can write, if we have these two states that we're going to work in, we're going to ignore everything else. We have these two states, say the two polarizations of a photon, then we can have the quantum state be some superposition of both of these two states. So it can be some amount alpha amplitude of 0 and some amount beta amplitude of 1. So it can be both things at the same time. And it's worth noting that the alpha and beta are complex numbers because the wave function can't be complex. And then the probability then to measure this, the photon or whatever this system to be in the state 0 is just proportional to the square of this alpha. And the probability to measure beta to be in 1 is beta squared. And of course, since they're probabilities, they have to sum up to 1, right? So there's a probability of finding the system in either of the two states has to be unity. So, so that's the one thing. And let's take again the example of polarization encoding. Here it's very simple to see that, we have, let's say 0 and 1 are the vertical and horizontal polarization. Then a diagonal polarization like that can actually be written as a superposition of half horizontal and half vertical. So like this. So we have the polarizations, and then we have, if we have half of it being horizontal and half of being vertical, we add the vectors together, we get exactly diagonal, right? So that's how you can add up to get the diagonal polarization, for example. And you need to have this 1 over square root of 2, because then when you add these two up with the square, half plus half is 1, so the probabilities add up, right? So that's how we can understand superpositions very simply when we're talking about polarization. But again, it works for all quantum states can be in superpositions like that. And yeah, this is a wave plate. This is how you, in the lab, rotate the polarization of light. So in terms of qubits, then we can write a message, for example, using these qubit values. So here's, for example, a message where we have zeros and ones, but then we have these weird things here, which are superposition states. So we can write a message using different ways, either in using this horizontal vertical way of writing it, or we could write it in terms of these diagonal states as well, or superposition states. And then we can choose to decode it in certain ways, where when we then measure it, of course, we're going to get, first of all, if we measure it as either horizontal or vertical, then we would get some outcomes which are, have to choose. So it has to pick which if it is 0 or it is a 1 or not. So once you measure it, it can be either one, or it has to choose which one it is, for example. Okay. Now we said what they can do, and here's another important thing is what they cannot do. And this is an important result for all quantum communication as well, is one of the things that qubits cannot do. What they can do is they can't be cloned, so they can't be copied. So it's called the no cloning theorem. Anybody knows why there's a sheep there? Yeah?
I don't remember the name of
Yeah.
the
first animal that was cloned was a sheep, so it's become like a symbol of cloning, apparently. Sheep. There's a conference called QCrypt, and that actually uses a sheep as a logo. One of the conferences some while ago, excellent, thank you, actually had, they took some pictures of optical setups, like small breadboards with some mirrors in a field with sheep around it, going around and smelling them. I don't know what they were doing. So it's become a really good joke. Anyway. Okay, so what is a cloning machine in quantum mechanics? Well, the quantum mechanical cloning machine takes a state that we're interested in copying, called psi here again, A, and then we have some other particle, which is particle number B, which is in some unknown state here. We're just calling psi. It doesn't matter what it is. Then after the cloning operation, we want both these particles to have the same quantum state. That's the code. We basically copied it. We have to copy it onto something. We can't copy a quantum state onto nothing. So we need to have some other system that, another atom or another photon that we want the state to be copied onto. That's why we have to start out like this with a blank quantum state. And now the reason, and this is very nice because this is sort of an important result, but it's super easy to show that this is not possible by using just very basic property of quantum mechanics, which is that it's linear. So one way to copy it is to say, let's try a superposition state here. Let's say that this state psi here that we want to copy is this superposition state. Okay, so we start out like this. This is our psi A, and this blank one here. We copy it, which means that we transfer this one over to here. So we get this state here. We just get 2 times the same. 1 over square root of 2 becomes 1/2 because we have 2 of them. And then we just say, well, let's just multiply, the terms here. 0 and 0 gives 2 zeros. 0 and 1, 0, 1, and so on. Right? So we have 4 terms here. Seems fair enough, but there's another thing we can do. Oops. We can do another thing is that we can first, before we clone, right? Because the cloning operation should work at any point. We can first multiply this 1 onto the psi, the 0 onto the psi, and the 1 onto the psi. So we start out like this, and then we do the cloning. So now we copy the 0 over to this one and the 1 over to this one, and then we get this state. And those 2 end results are not the same. So something was wrong. And the linearity, the fact that we can multiply into brackets and parentheses like this in quantum mechanics is a very important feature of quantum mechanics, sort of the way the all the equations, Schrödinger's equations are formulated. It has to be possible. So it must be that this assumption was wrong. We can't do this. So cloning in quantum mechanics is not allowed. And that means that if you have a quantum state, a system in some quantum state, there's no way that you can make another copy of it. It means that if you want to measure that quantum state, you also don't have the option of making many copies of it and then measure different properties so that you can get all the information about the quantum state. Basically, whenever you measure a system, you can only get partial information about that system. And your measurement, how you do your measurement, will decide how that works. So we'll get a little bit more into that because that's the basis of quantum cryptography. Okay. I don't remember what's on this slide, but we'll see here. Okay, what should they be able to do? It's a little bit more practical now. Well, qubits, their properties or what we want them to do depends a little bit, or how they should behave, depends a little bit what we want them for. And two important things that we might want them for is for quantum computing to do some sort of computation. And if they are to do some kind of computation, well, we need them to interact with each other. For example, in a computer, you will have AND gates or OR gates, right? And basically, in an AND gate, you take 2 bits into the gate, and it asks, are they the same? But in order to ask that question, you need to compare the two. So there needs to be some sort of interaction between these 2 bits. Electronically, in a computer, that's easy. But when we're talking about qubits, it basically means that they have to sense each other in some way. So you need some kind of strong interaction. And you typically get that from atomic systems, something that, has electrical fields or reacts to electrical fields or magnetic fields or some sort of interaction that's strong. And the other application you might want for qubits is you want to transmit them from one place to the other. So you want to send a qubit from one place to the other. So that's the communication part of it. And if you want that, well, then you want them to be transferred really fast and without much interruption. And so you don't want them to interact. So you want the opposite. And in that case, the choice is typically photons. Again, photons travel pretty fast, I've heard, and they don't interact much. That was my first thought yesterday when we heard the talk about black holes, where there was an example given of when the photons were emitted. It was back when the dinosaurs were alive, right? That's how far it traveled, and it didn't interact, at least not in a way that destroyed it, with anything on its way. You couldn't send an atom from that far back in time and then it reached Earth. So clearly photons do have some pretty neat properties that allows them to travel fast and not interact too much. Okay. So I think that was the basics of quantum information. Just to sum up, the very important aspects was superpositions. Photons or our quantum system can exist in different states at the same time, described by some probability amplitudes. And then the other property was that we can't copy quantum systems. And those are the things that we're going to use now for quantum communication. And in this quantum communication slide, it's going to be really short. So the first thing, what I'm going to talk about is just to say what are some of the applications of quantum communications. What do we actually mean when we say quantum communication? And it means a couple of different things. So one application or one use of quantum communication is quantum key distribution. So this is where you're able to exchange in a secure way. We'll go through that. So we'll hear much more about that. Information between different users in a way that you can show nobody interfered with your transmission. And that allows you to do cryptography based on principles of physics, which is always cool, but also better than some of the weaknesses that classical cryptography has. Ooh. When did we start? We started 2:30.
And by 3:45.
3:45. Already talked about it. Anyway, then we have distributed quantum computing. Basically, you want to hook up quantum computers at different locations. If that's going to make any sense, then they have to be able to be connected over a quantum link so that they're sort of quantum mechanically connected to each other. And then we have also some applications of quantum metrology, where you can enhance the precision of some devices that are separated by having them connected and sort of being part of the same quantum system. One of the first proposals was actually for astronomical observations with telescopes at different locations being entangled with each other. Again, relation to astronomy, but I think that's a very far out sort of like application right now. There's a lot of things that have that. And then tomorrow I'll talk more about this sort of application or sort of more of these things. So if you want to hear more about that, I'm here tomorrow. So that was it, right? I'm gonna go through this, okay, right? Now we have quantum key distribution. As I said, one of those applications that I really want to talk a little bit about. And why do we want quantum key distribution? So first of all, classical cryptography that we use right now is vulnerable to advances in computation, more and more powerful. Basically, you know, we hear once in a while you hear about now the supercomputer has cracked this particular security or this level, this length of a password or a keyword. And so they've advanced to a more longer, more complicated one, but it means you constantly have to find new ways and upgrade your key or your encryption. And sometimes actually your encryption has to be safer for longer than it takes to break the key. So some information, I'm particularly remember that the census data in Canada has to be actually kept secret for 90 years. Like there's no way that you can predict what's going to be kept safe for 90 years. So somebody can intercept your communication, just store it on a hard drive for 20 years and then say, okay, now we have the computers to crack it. Let's see who did this and this covert operation in some country or whatever it is, right? Could be pretty bad even 20 years later. Mathematicians are working too. I don't know what it is, but they seem to also find algorithms all the time. Some of them have the potential. There's been some steps towards actually developing algorithms that are more powerful at undermining the current encryption sort of paradigms. And finally, we have quantum computers, and quantum computers, which are also seeing a lot of progress, would actually go and undermine everything that we currently have in cryptography. There are new protocols I should mention before I start talking about QKD. There are other ways to overcome the problem of all of these things in cryptography. It's called post-quantum cryptography. So it's when you want to make it secure against quantum computers, which uses more complicated sort of mathematical methods. The problem with most of those is that there is no proof that a quantum computer cannot hack that as well. There's just not any known method that can do it. Right? So, and they're also very computationally heavy. So let's see what quantum key distribution is about. So we have Alice and Bob. They want to talk to each other. So the first thing to understand about quantum key distribution is you're not sending the message using quantum mechanics. You're sharing a key, a secret key. Okay, and so Alice wants to send this message. Anybody go in and search in Unicode, you'll see that she's pretty naughty. So the problem is that she might send this over a very suspicious neighborhood of some kind, and she doesn't want to disclose her message to anyone in there who might be trying to intercept it. So what does she do? Well, she takes this random key that Bob also has. So it's just a series of zeros and ones. She wants to now use this completely random sequence of bits here to encode her message. Because what she does then is that, so it's a secret key, right? Is that she just adds up binary addition of those two numbers. So 1 plus 0 becomes 1, 0 plus 0 is 0, and 1 plus 1 is 0, so your cycle, right? And what that ends up being is now complete nonce, it's just complete randomized now, the message. And this, of course, you can send over to Bob, because anybody who intercepts that message is going to read gibberish. There's nothing, no information in it. And then using the same secret key, he can now do the same addition. So if he does that addition, he actually gets back the message. So now they've exchanged the message, right? So that's how quantum key distribution works, or what the notion. So the important step is that the quantum part is to get this key here shared between Alice and Bob, and to make sure that nobody else knows that key. Because if anybody knows that key in between, then of course they can decode the message too. So that's what quantum key distribution is about. And the protocol I'm going to describe is the so-called BB84 protocol. So here's where I will deviate from Tony Leggett's, and hopefully it's okay. But this is actually the original quantum key distribution protocol proposed by Charles Bennett and Gilles Bassard. He's Canadian in Montreal, sorry, I'm always proud of that. And at a conference in '84, that's why it's BB84. And to get us started, we're going back to polarization and states, and we're going to describe some symbols here. First of all, as I said, we're going to encode qubits, ones and zeros, into different states. For example, we said we can have the ones in the vertical polarization and zeros in the horizontal. But now we're going to add one more step to it. We're going to say, well, we can also encode 1 and 0 into the diagonal and anti-diagonal polarization. They're different by a plus and a minus sign when you add them up. And if you look at these two states here, they're also orthogonal. So you could as equally choose these two to encode it in as you can choose this one. So we say that we have two different bases of preparing these qubits in. That's going to be important, that we have a choice of both the qubit value, 0 or 1, and the basis, either the plus or the x basis. I want to just briefly also comment on something that we're going to maybe, hopefully, get to a little bit later, is that there is alternatives of encoding qubits. As I said, any system where you have two values that are orthogonal can be used. And you could actually also take a photon and split it into two different discrete times, and then say that you could have a photon arrive at an early time or a late time, or you could have it in a superposition of an early and a late time, where you basically don't know where the photon comes in early and late, and you can have a phase between those two. Think of it like you can take a photon, take it through an interferometer with two different path lengths and merge it. Now when it comes out, it doesn't know which path it took. So it, the wave function will correspond to it having taken both paths. So those are both possible. And depending on the phase of those two paths, you will have either plus or minus. These are called time-bin qubits. And we'll get back to them if I can later on. For now, we're going to stick to the polarization basis. And so there we have wave plates and beam splitters to do the analysis and the rotations. And for time-bin qubits, we would have need interferometers, as I said, to analyze and create them. Okay, here's the QPD protocol. So we're going to go through a couple of steps, and we're going to see what happens and how do we use these different bases. So every single time Alice prepares a qubit, she chooses a basis and a bit. Plus basis, and one is vertical. So she sends off a vertical photon. She sends it with her favorite transmission here line, and she sends it to Bob. Bob receives the qubit. He chooses to also now randomly measure in some basis. He doesn't know, and Alice cannot tell him, so he just has to make a choice. In this case, he chose the same basis, and of course, then he will, by with a unit probability, always measure this to be 1. Right? Basically, if you put a polarizer, it would always be transmitted in this case. You would see that that must be 1. Okay, everything worked fine. So they chose the same basis, and then they can rely on this qubit because they chose the same basis. But we could also have a scenario where, Alice chooses to prepare in the other basis, the X basis. She sets it to be a 0, which is this polarization. Bob chose the other basis, and that means that now his measurement outcome is in a basis that is at a 45-degree angle with respect to the basis Alice prepared in. So his outcome could be either one or the other. It's really random what he picks, right? You can have 50% chance of projecting onto this or this, horizontal or vertical. In this case, it's horizontal, which he interprets as a 0. So actually, he did get the right value by chance of the bit, but he chose the wrong basis. So that's a problem, but we'll deal with later on. Okay, now we have another scenario here. Alice encodes a 0 in the plus basis. Bob again chooses the wrong basis. In this case, his random outcome is actually the opposite bit value. Okay, so both of them are wrong. And so they continue here. They both chose the same basis. And then Bob always faithfully recovers the correct bit value. Okay, and we just continue here. they have the same basis, correct bit value, correct basis, same basis again, they're on a roll. But oh, there we go. Different bases, random outcome from Bob's side. He happens to measure 0, which is not what Alice encodes, so you know both of them are wrong, both the basis and the measured bit value. All right, so we continue. Different basis, everything's wrong. Different basis, they happen to get the bit value correct, and continue right basis, wrong basis, right basis. Okay, so we've gone through, we've exchanged a couple of bits here, and the point is that you can see that every time they chose the same basis, you know, they do get the right bit value. When they choose the different basis, half of the time they get Bob gets the wrong result. So basically random chance of him getting the right result or the wrong result. So clearly, if he wants to know the random bit that Alice sent him, he cannot rely on any of the measurements where he chose the wrong basis. So at this stage of the QTD protocol, Alice tells Bob what basis she chose. So she doesn't tell him the bit value, but just what basis she chose, because that allows him to eliminate all the ones where he didn't choose the same basis. So they just erase those, you know. I'm not going to use them. Half of our data is lost, but you know, that's the price you pay for security. Okay, now what they have left is perfectly correlated, which is of course good, right? Because now they've done the first step of what's important for having a key. It has to be the same key. It has to be an identical key that they have. Now, this other part that it's secret, well, that's not clear yet why it is secret. So that comes in the next step of the protocol, or the protocol, because at the moment, it's only Alice and Bob. But hey, we have this suspicious neighborhood. Suspicious neighborhood killed the messenger. And now, things cannot be relied on. But the point is that this, we call it an eavesdropper or Eve, she has to, or they have to also measure the qubit somehow. They have to measure it. And in doing so, they have to make a choice of what basis they have to pick, right? They have to choose the plus or the X basis. They can't just leave it for later. So they have to make that choice. And so let's see what happens when somebody in between Alice and Bob has to do a measurement in order to try to figure out what the bit value is. Well, this is what happens. Okay, first time, she chose the right basis, she chose the plus basis, she gets this qubit out. It's a 1, which is actually the right one. And now, of course, she has to transmit something to Bob. Otherwise, he'll never measure anything, and he will just say, well, I never got any key. Then, you know, whatever information the eavesdropper has is useless because there's nothing that Alice and Bob thinks is correct. So she has to pretend that nothing happened. So she sends on the photon to Bob. And since everybody had the right basis choice, you know, everything went fine. No problem. Okay. Obviously, something is going to go wrong somewhere. And it's going to go wrong maybe here. Because now the eavesdropper chose the opposite basis. And they measure a 0. And since they measure a 0, they're going to send a 0, which is this horizontal, or this, the diagonal polarization. Let me just see what I have decided. And now, since it's diagonal polarization, it's actually random what Bob measures, right? He can measure either horizontal or vertical because this is at 45 degrees. So his measurement outcome is random. And in this case, it turns out it went onto the vertical projection. And so he thinks that that's a 1, which is not correct. So now we can see that the fact that the eavesdropper inserted themselves into the protocol gives a chance of getting an error in the bits that they exchanged. Okay. So we'll go on to the next one. Here again, the eavesdropper chooses the wrong basis. But in this case, you know, even though it's the wrong basis, there's a 50% chance that Bob still measures the right thing. And in this case, he does. Okay, fair enough, happens. In this case, everybody chose the right basis, everything goes well. Here, everybody chose the right basis, went okay. Here, the wrong basis, and in this case, again, it happened that Bob, you know, with the random outcome, gets the wrong outcome. So we see now that when an eavesdropper goes in, even though Alice and Bob chose the same basis, there will now be errors in the key. And this is what is important for quantum key distribution, because what two users will now do is that they'll go in and take of, maybe they have 100,000 bits that they've exchanged. They'll go in and look at maybe 10% of those, and then they'll exchange their measured values. And then they'll look at how many errors do we have. And if that error threshold goes above a certain level, then they'll be able to say that this key is not secure. We cannot trust it. If the error that they measure is below a certain value, ideally 0, but it's never going to be 0. But let's say that you could get 0 errors, then you can be sure that nobody has intercepted these qubits while they're being transmitted. And therefore, the random numbers that you have that are your key can be verified to be secure. So this is how quantum key distribution allows you to get a secret shared key between two users that are far apart by using transmission of qubits in single photons. Okay. Now, some practical considerations. Time here. Ooh. Okay. I'm going to go through this really quick, just because it's just some practicalities. The question is, how fast is quantum key distribution? Well, you start out by sending a lot of photons along, but then some of them get lost in the fiber. So you end up with, only some of them making it through the fiber. That's fine. If they don't make it through, Bob doesn't measure anything, and he's not going to care about those photons that were received. Then they have to do what we call the basis reconciliation. That's basically where you share what basis it is. You lose another half of your photons that way on your qubits, so you get even less. Then you have to figure out what is your quantum bit error rate. You have to take some chunk away and say, what is my error rate? Basically, figure out how secure it is. You lose some more, some number, or it could be some fraction. In this case, I just say it's a constant number that you want. Okay. What is the loss in an optical fiber? Well, that's just some exponential loss. So you can calculate what the loss is, and you can calculate what the rate is going to be. So it's about, what did I say, 4.5% per kilometer? Anyway, but there's a certain loss factor in optical fibers. Now, the point is that if there are some errors in your key, then you have to do error correction on those, because, if it's just not, too many errors, it could just be imperfections in the transmission channel. And if you do error correction, you can also kind of erase whatever information an eavesdropper might have, as long as it's not above a certain threshold. So you have classical ways of doing that. And here's where I'm going to maybe just very quickly say, let's say this is, so use what you call low density parity check matrices. You check what is not the property of each bit, but what is a property of some collection of bits. We talk about the parity of the bits. So let's say this is the random string, some section of a random string that Alice sent, some ones and zeros with some labels on. Then you have some matrix here, which is a parity check matrix that just multiplies different terms together of this string. So basically, you multiply this matrix with this string that's written up there, and you get some result that's just the sum. Every time there's a 1, you multiply with the value, and otherwise you don't have anything. So you just look at what is the sum of these values, and you get some, what we call a syndrome. So some numbers that tell you what is the combined parity of, in this case, 3 bits from different indices in the original string. And then if there are errors, let's say that for what Bob received has this error in it, one of them was flipped over here to a 1, well, then the syndrome that he calculates afterward is going to be different. And he doesn't know, based on this, you can't tell which ones are different, but there is a way then to go back and calculate which ones are the most likely ones to be different based on comparing with the values that he has, right? So the eavesdropper, if they intercept the message of the parity check matrix, the syndrome, they will know this information, But they won't know what Bob calculates, so he has unique ability, has more information to figure out without disclosing to the world how he corrects the errors. So, and here's, so I'm not going to go into this. Let's go quickly through that. But I just want to point out that because of this whole calculation, there's actually a limit that you find out. You have to do error correction. And then after that, you have to erase any information that an eavesdropper might have had. It turns out that the maximum errors that you can tolerate is around 11%. So it's very common with QKD people, quantity distribution people, that they always know that 11% is the maximum error rate that you can tolerate. If you have more than 11%, then you use up all your key to do error correction and to do what's called privacy amplification, where you remove any information that an eavesdropper might have had. So those are more tricky things. So let's just go through this. So here's an example of a protocol for. Here's an example of some experimental setup for polarization-based QKD, but let's. I wasn't planning on going too much into detail. So let me just talk about some of the vulnerabilities here on key distribution. And one of the things that we were assuming so far was that we're encoding these polarization states into single photons, right? So we had one photon with one polarization, and it turns out that it's very hard to make real single photons. You need basically some single atoms or single emitters, and those are very difficult to come by. People are getting better and better at making them, but basically it's not trivial. The easiest way to do quantum key distribution is to use a laser, then dim it down or attenuate it down to a level where there's on average less than one photon per pulse, because then the probability of having more than one photon per pulse is even smaller. So you basically say that your average photon number is like 10%, then every 10 pulses there is a single photon, but only once every 0.1 squared. So 1% is there 2 photons. So you kind of have something that looks like a single photon source, but it's not quite, right? So here's an example of what we call these. So if you have these laser, these classical kind of pulses of light with some photon number distribution, we call those coherent states. So that's mathematically written like this. And if you look at the probability of there being n photons in that, it has some distribution here, which is given by this amplitude alpha. So basically, there's a probability distribution. You can plot it for different cases here for average mean photon number of 1. Well, the one column here dominates. Here is for 10. Just an example, it kind of looks like a Poisson distribution, eventually a Gaussian distribution. And then just for comparison, you have other photon sources, for example, thermal sources. They will have a different distribution. And then if you have like a number state, which we call a Fock state, it has like just one pillar. All the probabilities of having only that particular photon number, right? So we want this, but we have this. And these ones are a problem. Why are they a problem? Well, that's because the probability, we said that you can't clone photons, but which is, if you have a single photon, you can't make copies of it. But if you originally sent off 2 photons, then you already have 2 identical ones, and then you prepared them, so you can prepare 2 photons from the beginning. It's just if you don't know what it is, you can't copy it. So if initially, you make the way you could, and then there's this, I should say, there's this proof that the information you can get, so we call it fidelity. How well can you get, what is the quality of the information between 0 and 1 that you get about the qubit is given by the number of systems you have. So here the n is basically how many photons do you have. And so if you have only a single photon, n is equal to 1, well, then you get 2/3. So you can get a fidelity which is maximally 2/3. basically the knowledge that you have of the photons can be, 67% of the complete information about the quantum state. You just, if an eavesdropper wants to know and measure that state, well, they just put this state detector and measure. Now, if there's 2 photons, well, you put in numbers, you get 75%. An eavesdropper could put in some kind of a beam splitter, put 1 photon here and put 1 photon here, and then they could get more information about the quantum state, and so on. We get to 80% when we have 3 photons. So having more than 1 photon in the beam of light or in a pulse, as you can get for the coherent state, is a problem for the vulnerability, for the security, because an eavesdropper can get away with knowing more about the key without disturbing it as much. So the solution to this, and this is just to highlight one of the basic sort of vulnerabilities, is and it's called the photon number splitting attack. And the solution to that is to use what's called the decoy state method. And that is beyond the scope of this talk, but you basically vary the mean photon number and make it impossible to hide the fact that you're attacking it, even though you're splitting off photons. So that's an advanced quantum communications. What was that? That was 0? I didn't, there was a simple.
Someone joining the papers.
Oh, I do have about 1 minute here. Okay, so I wanted to. And there are other attacks on quantum key distribution systems. There was a group in the University of Waterloo that was called the Quantum Hacking Group, and they devised all kinds of hacking attempts. Some of these are by them. And the main thing is to say that, well, the quantum mechanics may be secure, but we're saying that the detector does a certain thing when it detects a single photon, and only when it detects a single photon. But if you could make the detector do something else, well, maybe you could manipulate the detector to let it measure exactly what you want. Or you could even go in and do a sort of Trojan Trojan horse attack on the source and get the source to emit exactly what you want by, let's say, shining some bright laser light back into and destroying some things and then just messing it all up. So there are certain very ingenious attacks on the actual hardware where the quantum mechanics is sound, but it's just that your devices don't do what they're supposed to do. And those are called side channel attacks. So we don't go through the actual quantum channel, but go from the side. There are ways to think of even measuring with some radio frequency antennas outside the measurement device. What is the detector detecting by measuring the electrical signals, for example? You could think of it in that way as well. Okay, and that leads to some other protocols that are secure against more of these hardware attacks. And that's actually some of the research we're doing. So I hope I can talk a little bit about that tomorrow. And yeah, so as I had feared and kind of predicted, we didn't quite make it to entanglement, which is past this one here. There's plenty. So I mean, maybe we should have an evening session. So we do write a coffee table. But anyway, let's. So this became more a talk about quantum key distribution, which is one of the, for the most. I don't want to say basic, but one of the foundational protocols or applications of quantum communication. One of the first things that people typically think about when they think about quantum communication. And tomorrow I'll talk more about quantum networks. So let's hear if there's any questions to what we did manage to get through.
In the protocol of BB84,
Yes.
do usually the bases themselves are always orthogonal between themselves, or can you like change a bit the orientation so that even if you use the wrong base, you are lean towards another
Yeah,
result?
I mean, the BB8 protocol is like this, but there are other protocols that have been developed since then that, first of all, don't use polarization state. They use other kinds of encoding. Some of those encodings, even polarization, are not necessarily orthogonal. You can have you bias the bases by having some of them closer to each other, and then that, excuse me, can have some advantages. But yeah, it's a little bit tricky to explain. But it's not necessary in general for QKD, but for BB84, by definition, this is how it works. We also saw, or we heard from Leggett's talk that entanglement can be used. Entangled states can also be used for QKD because basically you just want to have two correlated measurement results. In this case here for BB84, you send a physical photon from A to B, and of course it's going to be correlated unless somebody measures it. But that's the point. That's how we find out that it's not secure. If you have an entangled state consisting of two particles at Alice and Bob, well, they're correlated perfectly too. And so a measurement on one will predict the measurement on the other one. So it's as good, as useful. So it's more technological question. What is the most secure protocol? The interesting thing in terms of the foundations of QKD is what assumptions do you have to make? As we saw here in sort of the last slide, you have to make assumptions about how secure or what kind of protection and knowledge do you have of how your devices make. You go to the end of the line of QKD, and there exists protocols that are called so-called device-independent protocols, which rely fully on entangled sources that you verify always are entangled. And you actually use something like a Bell state, Bell inequality violation to verify that your system operates in the quantum regime. And as long as you verify that it violates the Bell inequality, you know that everything was quantum. Any measurement anywhere, an eavesdropper would break that quantumness, so you can verify. So you verify your sources, you verify the transmission channel, everything. And then you don't have to rely on any assumptions.
Does it matter if there is an eavesdropper? Like, how do they compare them safely?
How they compare the bases? So what they say about the step where they have to exchange the basis information. The requirement of that strictly is that it has to be an authenticated channel. So you just want to know who you're talking to. If you don't know who you're talking to, at best, you cannot, you won't be able to remove any errors that exist. You just won't be allowed to have the communication. The point is that it's not, it's not a secure channel. The basis can be exchanged through a public channel. There is no requirement because at that point, if the eavesdropper has to have made the measurement already and resent. So at that point, she cannot go back in time, at least not with current technology, and change her choice of the measurement basis. So she made a choice, and now it's irrelevant whether they share the actual preparation basis.
Thank you.
Online questions? No?
Unfortunately, we don't have time for more questions. We have to close the workshop.
Well, that's the last thing. We would like to thank you for this workshop, Dr. Oblak, and also for the audience. And also, we would like to give you this diploma. And also, we would like to take the opportunity to thank our sponsors, without whom this event would not have been possible, Ternium, Climate AI, and HEV. And also, well, thank you very much for your presence, and see you in a few moments for Victor Yakovenko's lecture, Economic Inequality from a Statistical Physical Point of View, which will start at 4 p.m. Thank you very much.
I know everything. I'm happy. That's the point of the tour. Thank you, thank you.
Yo lo que me explicó.